In this video, we will explore the properties of immiscible fluids of differing densities. We will compare the time needed for the transfer of a specific mass and volume of the two fluids by varying the diameter of the transfer tubes.
Before we begin, we will have a short safety message.
Oh, I wonder if this is sharp. Ow!
When cutting straws, beware of dangerous projectiles.
What are you doing?
I'm drying the glue.
Why are you wearing safety glasses?
Because the fumes burn my eyes.
You have good safety etiquette.
For this experiment, we are using oil and water. We chose these two fluids due to their contrasting densities and immiscibility. As you can see, with the same volume, the water has a greater mass than the oil.
For the first test, our transfer tubes are 4 millimeters in diameter. We will use a stopwatch to measure the fluid transfer time.
The heavier fluid, water, is pulled down through one straw by its weight, displacing the less dense fluid, oil, which is consequently pushed upward through the other straw. You can see there are fewer oil bubbles in water than water bubbles in oil. This is due to oil's lower surface tension. The intermolecular forces holding together an oil droplet are primarily dispersion forces. However, a water droplet is held together by much stronger hydrogen bonds.
1 hour later. Later that same evening.
For our second experiment, we used a straw diameter of 8 millimeters and again, using a stopwatch, measured the fluid transfer time. As you can see, the bubbles are much larger and flowing much faster with the 8 millimeter diameter tube.
Three minutes using an 8 millimeter diameter transfers the same volume as an hour using a 4 millimeter diameter.
We began by taking the masses of an empty bottle and the bottles with the fluids in them. We assumed the density of water to be 1 gram per cubic centimeter to find our total volume. Then we divided the mass of the oil by the volume to calculate the density of the oil.
Our first test used a straw diameter of 4 millimeters and transferred 377 cubic centimeters of each fluid over the course of 1 hour, 51 minutes, and 16 seconds. We calculated the volumetric flow Q by dividing the volume transferred by the time. Following this, we calculated the velocity by dividing the volumetric flow by the cross-sectional area. Additionally, we found the mass flow of water and oil by multiplying their densities by the volumetric flow.
For our second experiment, we used a straw diameter of 8 millimeters. This resulted in a substantially reduced transfer time of 7 minutes and 14 seconds. We again calculated volumetric flow, velocity, and mass flow.
The disproportionately larger velocity in the 8 millimeter straw can be explained by the velocity distribution diagrams of the straws. The velocity through the smaller straw is more affected by shear force. Shear force is the frictional hindrance of the cross-sectional velocity. Shear force is maximized at the walls of the pipe and minimized at the center. In the larger tube, the center of the straw is further from the walls, resulting in a lower average shear force, therefore a larger average velocity.